This is the Absorbance and Fluorescence Lab report by Group 2B, Patrick Klaus, Patrick Hakela, and Nick Kufal. The problem in this experiment is that the dye concentration and the kind of dye is unknown, so we are going to have to try to find those. This is our goal. Our hypothesis is that we think we have the Lapidus dye because our dye was purple, and that dye had the least absorbance, around 400 nanometers. The results concluded that we have Lapidus dye, which was confirmed when we made our absorption graph, and it had a concentration of 0.0135 molar found using Beer's law. For the models in this lab, we have the photon model of light. This picture shows that when a photon is absorbed, an electron will move up energy states, and when a photon is emitted, it will move down energy states. Also, we have a system schema for our experiment. This shows that we only considered the dye as part of the system, and light was acting outside of our system. Our goal in this experiment was to find what type of dye we had and its concentration. We used a spectrophotometer to gather data on the transmission of light passing through the dye, which we used to calculate the absorbance in Excel by taking the log of the intensity transmitted over the intensity of the baseline. Then we found the emission spectrum by shining a light perpendicular to the fiber optics cable to compare with known values. From the known dye, we used the known epsilon value to find the concentration of the dye in the solution. For the dye solution, we passed light from the flashlight into the solution. It transmitted some of the wavelength through the fiber optics receptor. For the fluorescing solution, we passed light perpendicularly through the cuvette in order to excite electrons. As the electrons relaxed and photons were emitted at certain wavelengths, we gathered the data with the fiber optics receptor. We did this perpendicularly to prevent the transmitted light from being used in the data. We found the absorption graph by testing the light through water with no dye, or the baseline, and testing light through the dye to get the intensity transmitted. Then we took the log of the intensity transmitted over the intensity of the baseline to produce the absorption graph, which we used to determine that we had the Lapidus dye. For the fluorescing graph, absorbance differs from fluorescence because it measures how much of a wavelength gets absorbed, and the fluorescence measures the fluorescence for a particular wavelength. You can use absorbance to find the concentration and fluorescence to find the compounds in a solution. Smaller wavelengths come out of fluorescein when it fluoresces because the electrons relax and travel fewer energy states when they are emitted than when they were absorbed. For our calculations, we use Beer's law, which states that the concentration equals the absorbance over the length of the path traveled by light times the absorptivity constant. And this constant equaled to 43,000, which we found from the Lapidus dye was a known value. Then the length of path traveled is 1 centimeter, which is just the length of the cuvette. And the absorption was 580 taken from our graph. Doing the calculations, we got 0.0135 molar. And then the absorbance, as I said before, was the log of the intensity transmitted over the intensity of the baseline. For the physics of the absorbance, the baseline test found the wavelength of light that passes through the water with no dye. When it was added, some wavelengths are absorbed, only transmitting the wavelengths that our eyes perceive. The spectra of light transmitted can be compared to the baseline to find the absorbance of the dye. For the physics of the fluorescent dye, when a solution fluoresces, an electron is initially excited by light energy to a higher energy state. After this, it relaxes back to its ground state and a photon is released. The wavelength of the photon is determined by how many energy states were jumped. The energy of the system is not conserved because we chose our system to not include the light source. The flashlight put energy into the system and it was converted from the photons to the electrons. When the electrons relax, energy is converted back to light energy, but with a different wavelength. For our errors and limitations, the distance to the spectrophotometer may have been a factor. We could have measured the dye at slightly different distances, skewing the data. Also, the amount of light and strength from the light source would have skewed the data if there is different amounts of light for the different experiments. The fiber optic cable is small, so there's a chance for inaccurate results because it is possible that the light source and fiber optic cable were not aligned properly. Holmes Hall water is not clean or clear, so that could affect the results. Also, the flashlight was not working properly. As we said before, the amount of light could skew the data, and our flashlight was flashing on and off at times. In conclusion, the dye had a concentration of 0.0135 molar, which we found using Beer's law. The dye was Lapidus, which we found from our absorbance graph, and fluorescence is caused by photons being emitted when electrons relax.